Hey guys, so today we're going to do this DFS algorithm that we talked about in the theory video. So as usual, I'm going to run through, I'm going to knock that code out, and then we're going to go through the notes after looking at the implementation, right, and what it looks like. Okay, so let's get started, and man, I'm going to try to keep this one less than 15 minutes. That seems to be my standard. I need to break it. I need to get shorter with this. All right, so first thing, we got to see the thing. All right. Then we're going to do a struct called graph, which is going to contain our adjacency list, like we talked about. Okay. And then that's going to be a hash map containing a string and a vector of strings for value. So what is this doing? Well, so this is the name of the node, and this stores its children. That's it. All right. Implement. And so this is going to be a constructor. For the graph, for the adjacency list, we're just going to do a new hash map, an empty one. Now this one's pretty cool, right? So add edges. Okay. So we need a mutable reference to self because we're going to be messing with the list, and we need a source node, right, and a destination node. So what this is going to do is this is going to create edges between the source and the destination. Okay, now check this out. Okay, so we're going to do entry source.toString, or insert with new, or now what's this doing? So this is really cool, man. This is doing a lot for you. This is one of the reasons, man, that I find algorithms so easy to just implement in Rust, because it handles so much of this tedious stuff for you. Okay, so entry, what entry does is entry returns an enumeration with two variants, occupied or vacant. Okay, and it works on hash maps. So what it does is you pass it. So what you do is you do source.toString, right? So that's our source node. Okay, and so entry, if it doesn't exist, insert with is going to create, so if it doesn't exist, this is going to return vacant. Insert with is going to create a new vector to store that. Then if it's not, then it's going to push that new node into there. If this returns occupied, this is going to return a reference to that occupied node, and then you will be pushing the children onto that node, and it handles all that for you. It's awesome. It's ridiculous, and it's just 4 lines of code, man. It's sick. All right. So let's do DFS, and then we're going to have a helper function that does the recursive bit. Right. So here we're just going to pass self and start. Okay. Now let's go ahead and do the recursive part. Let's go ahead and implement it. Okay. And then here we need to do self because we need to access the list, and then node, pass it a string reference, and then visited is going to be a mutable hash set containing unique strings. Okay, so a hash set is just a set of unique things, right, based on the type. Okay, now DFS, so let mute visited. This is going to be our hash set, our new one, and then we're going to do DFS recursive, and we're going to pass start and a mutable reference to visited. Okay, now here, so this is where the magic happens. Stupid saying. So if visited.contains node, do return, and then visited.insert node, right, because it's not there. It needs to be there. We got to put it in there, and then we can print out the things that we have visited. Right, now I'm gonna give you a little bit more room. So now we're going to do No, that's right. That's it. That's the only method that we need. So now we can do the for loop. While some neighbors equal dot get node, okay, we're going to say, oh, while let, don't forget that. So now we're going to say for neighbor in neighbors. And what we're going to do is we're going to do a recursion on this, right? So that's going to be neighbor and visited, okay? All right, and that's it, guys. 40 lines of code. And so all we're doing here is we're populating the list, and then we're going to be traversing it, right? That's the point of this. Okay, so over here in main, I have a little implementation going. All right, so we've got add edge. Okay, so over here in main, we're creating a new mutable graph. We're inserting edges between these nodes. You can see the source and destination. We're printing the graph so we can see it, and then we're actually printing the traversal starting off from A. Okay, so fire that off. Oh, and it looks like we have an error. Let's go see what's up with that. All right, so let's go back. Let's see what we got. Let's see. Oh. Yeah. There we go. Honest mistake. Okay. Gotta watch that. You gotta watch those whiles and those ifs. All right, so you can see here we've visited all of our nodes, and so this is our list. And remember, guys, this is a hash set. It's not going to come back in order, so don't freak out when you see it like this. So let's make sure everything is there, right? So we've got A connected to B, right there. We have A connected to C, right there. B's connected to D, right there. C is connected to E, right there, and D is connected to F right there. Okay, so we're good. We are successful. It gave us everything that we're looking for. Okay, now let's do a little bit of a deep dive with this here code. All right, so depth first search. All right, so the first thing we do is we define that struct that just holds the adjacency list, right? That's all that this does. The string is the name of the node, and the vector of strings is its neighbors, okay? The constructor method, all we're doing is creating a new hash map. Nothing crazy. Now, adding edges. So let's go into this a little bit, okay? So now, edges are connections from one node, the source, to another node, the destination, okay? And so in our adjacency list. Now, entry. All right, so this is a Rust construct that returns an entry enumeration with either the occupied or vacant variant. Okay, so if source.toString, the key, already exists in the hash map, entry will give us a handle to that existing entry. So that's when children will be added, right? Because we're going to get a reference to that occupied node, and we're going to add children to it. If it doesn't exist, entry is going to return vacant, okay? And so we're going to create or insert with will then create a new vector and insert that node in there, right? So if the node does not exist, entry returns the vacant variant, right? Or insert with creates a vector to store that node in and then inserts it. If the node does exist, entry returns the occupied variant, and then insert with returns a reference to that node and push inserts children into that node's reference, right? It handles all that for you. That's what's so great about it, okay? So here's an example of inserting the edges. This is just a walkthrough, kind of how the edges, how everything kind of builds out, right? You can look through this. And what I want to get to is down here to the visualization, right? So we can actually show you how the traversal works. So this is how, this is probably how you would see this in your head, right? Like a standard graph representation like this, okay? So we go into, you can look in here for the technical details and everything, but I'm just going to walk you through this, okay? Now, so what the way that this works, okay, is, and we'll go into the beneath in a little bit, but this is what is important to understand, right? So A is inserted, okay? So A is inserted, and then B and C are inserted, right? Then B gets D, C gets E, and then D gets F, right? So that's how it's constructed. Okay, now when it traverses, we're going to traverse down the left side first and then down the right side. So what's going to happen is we're going to create A and mark it as visited. We're going to go back through, see that A is there, so we're going to append B to it, okay? Then when we insert B to D, we're going to go in, A is going to be there, B is going to be there, it's going to be visited, and then we're going to insert D, and then the same thing for F. Now, F is at the end. So what happens is we go back. We go back. Does D have any neighbors? Nope. That are unvisited? Nuh-uh. B, any neighbors unvisited? Nope. A, neighbors unvisited? Yep. C. And then we do the exact same thing down the right, and then we go back up. And then when we get back up to A, we know everything's going to be visited, right? So, the DFS method, okay? So, like I said, the hash set is a data structure that stores unique elements, right? So this is going to store the nodes we have already visited, okay? Because there should not be any redundancy there. They should all be unique. We only want to visit the nodes once, okay? Talk about visited a little bit here. Now, the recursive logic, okay? So the redundancy check, that's, whatever, man. That just means everything's been visited, okay? And then, so then after that, we mark the node as visited, because you got to think, right? So what's going to end up happening is if the node isn't there, we need to mark it visited immediately, because that node, that's just how it works, okay? If the node's not there, we mark it visited because we're dealing with that node, right? And that's when we print it out, okay? Now, what the loop does is the whole point of this loop is to explore the neighbors, right? So, and right here, I talk about the if-let pattern matching thing, where I put while, and then so the get node, this is important to know. So self.adjacencylist.get node, this returns an option, right? And so, right, because some, okay? And so if the node exists in the adjacency list, get will return something, and that something, well, it's a reference to a vector, like we talked about. And then if the node doesn't exist, it's going to return num, right? That's what option does. It either returns something or it returns nothing. And then the loop states that if get node returns something, then we will call that result neighbor and run the code block, right? So all we're doing, the recursion, all we're doing is just checking to see if those neighbors have been visited, right? And then, so if we have neighbors, we iterate over each neighbor, do the recursion, and then that's what does that deeper thing that I talked about earlier, right? Where you go down and back up, down and back up. That is the heart of this DFS thing, right? So this, I've already talked through this earlier. I told you guys, what's happening. This kind of steps through that. This goes through the flow in a little bit more granular fashion, as I usually do. And yeah, guys, that's it. And so that's the basic implementation of this. We'll be revisiting. So guys, all of these algorithms I'm going to be revisiting. Don't think that these are done. We're going to be revisiting these. We're going to be adding methods to them. We're going to be doing optimization stuff. I mean, this algorithm design stuff, man, this algorithm implementation stuff, this is going to be a whole series. I plan to have this be very exhaustive. So yeah, so it's not going to stop here. We're going to make all this stuff as performant and full bore as possible at some point, right? All right, guys. Well, that's it. Thanks for tuning in. And, ask those respectable questions to get those respectable answers, and help each other out. Let me know if you have any questions, and I'll see you in the next one.